Well, hello again everybody, and today we're going to have a look at the second board that our customer returned. And from what the customer's described, it does sound as though it's got some form of intermittent fault. I'm sure you will know that these kind of things can be the very devil to try and track down. So the first thing I've done is actually just had a bit of a visual look at the board, and I can't see anything particularly wrong with it. I can see a few scratches on it here and there. I might just touch up the conformal coating before I send it back. Nothing particularly obviously bad. Looks like they've had a go at replacing some of these relays in the past from the looks of the conformal coating. A few bits of what looks like corrosion on, what is that, on some of these sill packs. I don't know if that is corrosion or again, have they possibly been replaced or touched up? Looks as though they've been changed at some point. So we've got these big, large smoothing capacitors because there's two 24-volt circuits which are separate on here. And each of the 24-volt circuits has got its own main reservoir capacitor. And looking at them, they are, well, they're 10,000 microfarads at, where's the voltage? 35 volts. Yeah, 10,000 microfarads at 35 volts. And what I'm going to use to check these capacitors, I'm going to use this Peak Atlas ESR meter. And for those playing along at home, it's the model ESR R70. I've had this quite a while. It seems very good. And all we have to do is just switch it on and it should do an automated test. It should give us a measurement of the ESR and also the capacitance value. So that's 0.04 ohms, sorry, 0.04 ohms in fact, at 9980 microfarads. Now I'm not really too bothered about the actual reading. I mean, the ESR value is probably about right. I'm not even going to bother to look it up on a ESR chart. I'm sure it's in the ballpark. It isn't coming up as like 1 ohm or something like that. It's looks pretty low, that, to me. So all we'll do is we'll just compare that to the capacitor next to it. Because let's face it, these electrolytics are always a prime suspect, and probably the bigger electrolytics are the worse. So this one has only got an ESR of 0.03, so it's a little bit better, but the capacitance is the same. That's 9980. So yeah, it's in the ballpark. I don't suspect there's anything wrong with that. Now there's not actually that many electrolytic capacitors on this board, but these small ones in my experience do tend to be more reliable, and I'm not really suspecting we're going to have any problems with them. But I will just test these two capacitors here, and I'll just check the ESR reading as well, because I guess it might potentially be more important. I'm not sure which of these is which. I think this one here, this capacitor certainly, is probably associated with the operation of this DC to DC converter. So the purpose of this is to drop the 24 volts down to 5 volts to power all the logic. So any kind of switching regulator, switch mode power supplies, etc., it's quite important that for the supply to operate correctly you need capacitors that have a low ESR. So we'll go ahead and check them, but I'm not going to make you watch that because it's not very exciting, is it? So I'm just going to check the voltage across both these main reservoir capacitors. Now I would expect to see a little bit of difference between the two of them. I mean, it's always quite a good test if you've got a transformer that's got, you know, the same output windings, just to do a measurement across the output windings. I mean, I think it's probably more important for a centre tap transformer. But what we'll do is we will just take a measurement of both the voltages across these capacitors, just to see if they are roughly or near enough the same. Now, I wouldn't expect these two to be exactly the same, because knowing how this circuit operates, one of the 24 volt supplies is used to run all the internal logic and stuff like that. So that circuit will be loaded, whereas the other 24 volt supply is just being used to run some auxiliary stuff, and there's no auxiliary stuff connected. So I don't know which way around it is, but I would expect one of these supplies, either that one or that one, to be a bit higher. Let's just power the board up. and that's 27.95 volts. A little bit tricky to do this because I mentioned before, everything's got conformal coating on it, and you've got to try to you know, ram your pointy thing through the conformal coating. So what was that? In all my jabbering, I forgot what it said. Come on. 27.91. Let's check the other one. 27.35. So what's that? About 0.6 of a volt difference. Yeah, from memory that's about typical. Okay, let's just put the meter onto AC now, and again we'll just see if there's much difference in the ripple voltage between them. So that's indicating about 4 millivolts ripple, so nothing wrong with that. And 16 millivolts ripple, which is slightly higher than I would have expected, but yeah, it's in the ballpark, that, isn't it? 16 millivolts, it's not the end of the world. So I think the next thing we'll do is we'll just have a quick look at the 5 volt supply on this board, which I think I'm just trying to think the easiest place to get at it. I think it's probably here. So 4.971 volts. So again, 5 volts. That's pretty good. And maybe we'll just have a quick look at that on the scope as well. Never sure, are you? You see that? Yeah, looks all right. I'm running this from an isolated supply anyway, but yeah, I've blown lots of things up in my time by attaching the scope probe ground to the wrong thing. I'm trying to think, is there anywhere better I can get a better ground off? I think this connector is at one of the auxiliary outputs, and I don't know if it's on the same ground or not. Yeah, it looks like we can get a ground off there, so again we will go for that maybe. I'm taking a guess here that some of these little spikes that we can see are just the ringing from the switch mode power supply. But what's that? I mean, it's nothing, is it? 100 millivolts, and yeah, that doesn't worry me at all. That's absolutely fine. Digital circuit, microprocessor running, nothing particularly excessive there. Well, I'm sure you've all seen on the EV blog the DaveCAD software. Well, I'm afraid the pricing of DaveCAD, it's just totally extortionate. So I've just got a cheaper open source version that we're going to have to use called ChrisCAD. So I thought what we could do is we could have a quick look at the inputs. And I'm not exactly sure what this circuit has got on it. So again, I'm going to take a little bit of a guess and think back to what we might have put on here all those years ago. Bear in mind what I'm drawing here might not be exactly right, but I'm sure it will be near enough. Each of these inputs has got 2 terminals on it, so let's draw 2 terminals there. And from memory, we've got a dirty great resistor there, which is a big 2-watt or something, these down here. And looking at them, what are they? Yellow, black, brown, or brown, black, yellow even, so that's 100k, isn't it? 100k resistor. And then we go into these sill packs. So then we've got, from memory, got another resistor like that. Don't know what value they are, and I can't see what the markings are, so we'll have to guess. Don't know. And then we go into these little pale face devices here, these opto-isolators. So let's draw a box for the opto-isolator package. And inside this opto-isolator we're going to have something, we're going to have some LEDs, aren't we? So I'll draw one LED like that. And from memory, these opto-isolators have got 2 LEDs in them, so we'll draw another LED there, and then they will be a transistor, won't they? So I think we probably take that out, and what do we do? Well, I don't know, maybe we tie it to ground, I can't remember. Take the other leg out. I'm going to assume that pulls up to 5 volts, but I really can't remember. And then I think we feed that out of there, what do we do now? I'm going to guess we've got another resistor, and I'm going to guess a capacitor for some low pass filtering. And then again, typically I suspect what we did was we went into a Smith trigger. I can never draw the symbol for a Smith trigger. It's something like that, isn't it? So, okay, so how does this work? Well, typically these inputs are 100 volts, and every input has got its own separate circuit, which is all opto-isolated. I think I might have said in one of the other videos, we kind of use 100 volts because back in the day that's what everybody else used to use as well. As time moved on, this board went through a number of revisions, and certainly the new one that we use uses a 24 volts DC, which is obviously much safer and much less likely to give you an electric shock when you're jamming your jammy fingers in it. Typically there would be some limit switches or something connected to these inputs here, and that would be fed via a 100 volt supply. So the power comes in, and we can't supply 100 volts directly to these opto-isolators because they would explode. So we drop that down to, I don't know, a few volts. And well, of course, the main thing these resistors doing are actually limiting the current through the devices. So, you know, I always get confused between dropping voltages and current. So, you know, resistors really, they're limiting the current, aren't they? So they're going to limit the current to something that these tolerate. And again, can't remember what that is. But I often think the only really interesting thing about this circuit here is perhaps the back-to-back diodes, because you might think, well, why don't you just use one of these LEDs? Because I should have drawn the arrows on them, of course. It's LEDs. And so the main cycle comes in, and what should we draw it? Let's draw, so that's the positive half cycle, and that's the negative. And again, I suppose I should have said that these inputs are, well, they're AC or DC, but as it happens, they're actually AC inputs on this board. So what happens on the positive half cycle, of the mains, this diode will light up, and on the negative half cycle, this diode will light up. But the main reason that that's done, you might think it's so that we activate this transistor on both sides of the main cycle, and it does do that, of course, and of course it has an effect on what the low pass filtering is that we need to set up here. But probably the main reason that you have these back-to-back diodes in one of these packages is, well, it's for a different reason to that. And the reason being is that LEDs don't like a high reverse voltage. So if you didn't have this, second diode, for example, this diode would be perfectly happy on the positive half cycle, but on the negative half cycle it's reverse biased, and there is normally, if this diode is in place, the voltage across this diode will be clamped because this one goes into conduction. But if you don't have that diode there, this will potentially see the the peak reverse voltage of, well, whatever the peak is of 100 volts RMS. And I can't remember what the typical reverse voltage is for a diode, but it's not particularly high. So what you quite often see is you will see these opto-isolator packages, and they either have two diodes in like this, or sometimes you'll even see somebody just fit an external clamping diode outside the package. So that's why they do that. The other resistor, which I didn't mention, which is embedded in the sill packs up here, what that's for is it actually just allows us to bleed some current off, because what you find with different LED packages or different opto-isolators, they have a different, I'm trying to think what it was, I wanted to call it CMR, but I think is it CTR? I think it's the current transfer ratio, which is basically how efficient they are. And what you can find is that even if you get little bits of current trickling into here, which you can get just from capacitive coupling in the mains wiring, what can happen is it can bring these LEDs on, and it can bring them on at surprisingly little currents. I've seen these things try to conduct at microamps. So what you have to do is we have to put a resistor here just to bleed off that current, so that these don't actually operate until this supply voltage comes up to something reasonable. And again, I can't remember what we preset these for. Off the top of my head, I'm going to go for 70 volts, but I really can't remember what we designed this for. So what I think we can do is, it'll just be quite a good laugh to connect a power supply to each one of these inputs and actually see what they come on at. So we should be okay. So let's switch on and switch on this power supply, and in theory I think I should be able to turn that up. And because I haven't done this for a very long time, I'm going to monitor the situation quite closely. So that's 15 volts. Is anything getting hot? No, it's not. Let's go a little bit higher. 30 volts. I can't remember where they start to conduct at. I wouldn't even like to guess. I just can't remember. It's been that long. Maybe something like 70 or 80 volts. 70 volts. Okay, so 70 volts is enough to bring that on. Let me bring you in on this LCD. Okay, so this display that I'm looking at the moment, this is the one that I can see the state of the inputs on this board, and I can actually also see the state of the output. So this is the one where I was pressing the buttons on to make the relays fire off. But we can also see the input. So at the moment we can see that input, it just says input. If I switch the power supply on, input 12 has come on. So all I'm going to do is see at what threshold they come on at, and just to see if there's any gross differences between them that might indicate a problem with the input circuit. So that starts to come in about 60 volts. So 12 equals 60 volts. Just turn that off. And I'm going to move to the next input now. Okay, number 11 came on at 62 volts. Okay, input 10 has come in at 61 volts. These are probably all, well, these are all on one package. I'd expect that when we move to the next opto-isolator along, we'll probably find a slightly different voltage. So all the LEDs and the photo transistors in this first bank of opto-isolators, they'll all be pretty closely matched because it's from the same batch of components, but maybe when we move on to the next set of opto couplers, we will find something slightly different. See, that one's come on a bit higher actually, so it's called me a liar again. So that one came at 68 volts. That one's come on a bit higher again at 71. And I think now the last one, which will be input 1. And input 1 came on about 64 volts. So basically we've recorded all these inputs, and all the inputs are working, and the on threshold is all within 10 volts of one another. What I thought we might find is one of the inputs that was maybe taking a much higher voltage to come on, and maybe there was, maybe there could be a problem with an input. But as far as I can tell, and it doesn't mean that there could be some other problems that I can't detect here, but from everything I can tell, this board is working perfectly well. But as I say, this is part of a bigger system. This is just one board that's part of a bigger system. But I would typically suspect that the problem isn't the board. I would suspect that it's possibly a problem with the network or the termination of the network. Or again, because I know the system works, one of the things that the system does, it monitors a door, and 9 times out of 10 it's a problem with a door limit switch that causes these intermittent problems that they're recording. Doors are the bane of my life. You would think a door can be open or it can be closed, but the problem with doors is, and especially big doors, is they blow around in the wind and they very easily go from open to closed and closed to open. And probably the greatest number of kind of false call-outs and problems we get reported are to do with bad doors. Yeah, that's all I can say. This board appears to be working as well as I can test it here. So I will package it back up and we will send these back to the customer. So I think until next time, that'll do. Thanks for watching. Bye bye for now.